Great. Welcome, everyone. This is the second edition of this year of the Frontier Seminar from the High Energy Astrophysics Division. My name is Javier Garcia. I'm Executive Committee member of the HEAD, and I'm together with Carolee Kearns and Drew Miles, we're organizing this seminar series. And the main objective of this is to provide a platform for especially younger researchers, students, postdocs, etc., to have the opportunity to present their research in a cadence, in a shorter cadence than just waiting for the actual HEAD meetings in person. So you might remember this started during the pandemic lockdown, and it has been very well received. So we decided to continue with this format. So the idea is to have these seminars. So far, we're thinking about about 3 months. We are going through the nominations carefully. We're trying to choose a diverse group of speakers, both in terms of gender and seniority level, and even expertise. But we encourage you to please keep sending your nominations, or you can also nominate your own students or colleagues if you think there will be benefit from this. Today we have 3 speakers, and each talk is gonna be about 30 minutes plus a few minutes for questions. You can obviously wait until the end of the talk to raise your questions, raise your hand virtually and speak, or you can also post your comments or questions in the chat. Okay, so our first speaker is Daniel Bretthauer. I hope I pronounced that correctly. He's a 4th-year graduate student at UC Berkeley, working with Rafael Amarguri and Dan Kassen as a NASA Future Investigator through the FINESS. Daniel works on theory and observation of kilonova short-lived optical IR transients powered by the radioactive decay of the heaviest elements on the periodic table that result from compact object mergers involving neutron stars. The title of his talk is Impact of Systematic Modeling Uncertainties on Kilonova Properties Estimation. Daniel, go ahead, share your screen, and you can start.
All righty. So thank you so much for having me here. As was mentioned, I'm going to be talking about my paper that just survived peer review very recently. That's all about the systematic modeling uncertainties of kilonova property estimation. So a little bit of background first. So what are these kilonova? So as kind of briefly mentioned in my intro, kilonova are these very fast evolving UV, optical, and infrared transients, and they're powered by the radioactive decay of these rapid neutron capture or R process elements. And so those elements are anything that's above something like atomic number 30 or so. And so these are some of the heaviest elements in our universe. And so these things are very important because these are, our kilonova are the only confirmed R process sites that we know of. There are still a few theoretical ones that have yet to be confirmed, but as of now, these are the only ones that have been confirmed. And so these things tend to come from either binary neutron star mergers or neutron star black hole mergers. And we usually like to think about our kilonova as coming in kind of 2 components in the same thing. There's the red kilonova, which I'll talk a little bit more about later, and the blue kilonova, which have, and their colors are based on their opacity, which I'll kind of get into what's going on later with that. So I know this is I'm new to this audience, so not a lot of you know me, but one of the things that I'd like you to know about me is that I really like to bake. And so I like to think that when I go to conduct my science, that I really bring the mindset of a baker to how I produce my kilonova simulations. Because in baking, you see, you need to be very precise with all of your measurements of ingredients, following the recipe. And then all of this is to ensure that the correct chemical reactions are occurring at the right time, the right amount, all of that kind of stuff. And so simulating kilonova is really not that different because you need to be very precise about what your kilonova ingredients are. And in this case, it's Things like how much mass is there? How fast is that mass moving? How is the energy being injected into our system? What composition are you using? And then also some nuclear physics things. And so the problem, though, is that when you have an incomplete recipe, because, for example, if you're trying to bake a cake, you know that you need to include flour, but if you have an incomplete recipe, do you add 1 cup, 4 cups, something in between? And so, there's incomplete knowledge when it comes to simulating kilonova as well, just like an incomplete recipe that requires us to make a whole lot of assumptions, which is totally fine. There have been a whole lot of papers that state assumptions that they make. They fit the most famous kilonova from GW 170817. They present their error bars based on their models. But the problem is that those error bars don't include the uncertainty in the model itself due to the assumptions that they make. And so I've listed a few of those assumptions here that we often have to make when we're running these simulations. Things like, what is the density profile of our ejecta? What is the R process heating rate? What composition are you using? What is the decay energy thermalization in your ejecta? What atomic data are you using for these simulations? And there are so many more. But for the work that I'm going to be talking about, I mostly focus on these last 2 things here, the thermalization efficiency and the atomic data. And so specifically with the atomic data, the problem comes down to the lanthanides, because these are very, very complex elements. They're the very bottom row of the periodic table. And so what's so complex about these things is that they have valence F-shell electrons. And so this means that they have incredibly high opacities in the optical and the UV. And so they reprocess a lot of the optical and UV light into the infrared that we see that makes our characteristic kilonova infrared excess. And so that infrared excess is a signature of the R process that has happened here when you have strong enough R process. And so when you have, kind of when I was talking about earlier, those blue kilonova, that's where you have very little of these lanthanides. Versus the red kilonova, you have a whole lot of these lanthanides intermixed into your ejecta, and so you get much redder and redder colors. And so, as I said, these things are very, very complex, and so it's very difficult to theoretically model these things, and so that we can use them in simulations, and that introduces a source of error into a lot of our models. And so I'll briefly put this up, but please don't memorize any of this. And if you have any questions, I'm more than happy to talk about each of these data sets later. But just kind of understand that for this work, I took 3 data sets from across the literature. I've color-coded them orange, blue, and green. And so anytime you see orange, blue, or green, those are the 3 different atomic data sets. So then the other thing that I mentioned is this thermalization efficiency. Because as your R process material is radioactively decaying, it's not just directly inputting the energy, it's not immediately heating it up. It's spitting out things like beta particles, alpha particles, neutrinos, gamma rays, all this whole zoo of particles. And each of those have to interact differently with all of the material around it. And that is what goes on to deposit the energy. And so you have to ask yourself, what is the fraction of energy that is actually going into the ejecta and heating it? And that fraction is our thermalization efficiency. As for example, the neutrinos, those are almost always going to stream away immediately. And so you lose something like 35% of this energy right off of the bat. And so there are 2 approaches that you can take in order to kind of try to prescribe this in your simulations. You can either say that no matter where I am in the ejecta, every single place has the same exact fraction of energy that's being injected into it and making it into heating the ejecta. And so this is what I call the global thermalization prescription, because every single place, no matter where you are, has the same efficiency. Or you can take the approach and say that, well, because my R process decay is producing gamma rays and these beta particles, the more dense the region is, the more likely that they're going to be absorbed and deposit their energy. And so you can instead have a local density-based approach where you say, hey, the denser the region is, the more likely it's going to deposit its energy. And so there are those 2 competing prescriptions for thermalization. So in order to study this, I use the Sedona radiative transfer code. I ran a whole grid of models of varying masses and characteristic velocities with 3 different lanthanide mass fractions that kind of span the entirety of the expected phase space of kilonova emission. And again, if you want any more details about this, happy to talk about it later. But So to kind of get to the punchline here, so here I have a time series of my kilonova models. And so here, this is the exact same ejecta parameters. I have 0.01 solar masses traveling with a characteristic velocity of about 10% the speed of light, and it is composed of 1% lanthanides. And so you can see that the spectra evolve quite differently. And I've also put the JWST filters here in the background to kind of give you a bit of a better sense of where all of this is happening. And so at very early times, things tend to be relatively similar. You can have a double peaked spectra peaking around like 1 micron or so, but things begin to rapidly diverge all the way to the point where at 10, 15 days, these things are not even qualitatively similar. And so that poses a very big problem if we're trying to derive just how much lanthanides there are in our ejecta, and therefore try to answer questions like, can these neutron star mergers be the dominant site of our process in our universe? Are they able to produce enough all of our process material that we see in our universe? And so you can begin to quantify these things. And it turns out that when you kind of look at the light curves, I have, for example, a couple of LSST bands up here, and then a handful of JWST bands, as well as the bolometric light curve down here, that the colors and the decay rates are the most severely impacted by your choice of atomic data set for your high lanthanide material. And so, and particularly, your blue filters are going to be most affected here. And the difference in color between these things is something like 1.5, 2 magnitudes. So there is a gigantic scatter just purely coming from uncertainties in atomic data set here. And similarly, the decay rates of each of these bands is wildly different. The only time that they get reasonably close, within about like 0.1 magnitudes a day within each other, is once you get to like Z and Y band of LSST. And again, our near infrared and our mid infrared colors or magnitudes, are wildly different, 2.5 magnitudes. And so the problem is that these are some of the most important pieces of atomic data, because this is how we can try to identify what elements there are in these, what elements are being produced in our kilonova. That's where we're most likely to be able to identify what elements there are present. So then also, so I've been talking about the uncertainty from atomic data. We can also speak to the uncertainty from the thermalization prescription, because you can try to compare your bolometric luminosity, since your thermalization prescription speaks to the total amount of energy that's being put into your system. And so what you can do to compare these things is you can ask, what is the bolometric luminosity from the global prescription of a particular model, and what is the bolometric luminosity of the local prescription of that same model? And then you can divide the two. And so in this figure here, I've split our models by their characteristic velocity. And again, they're color-coded by their atomic data set, and kind of the lighter colors are the lighter mass models. And you can see that this ratio is not 1. And so this means that because your mass estimates are most closely tied to your bolometric luminosity and overall brightness, that your choice of thermalization prescription is going to result in a difference of something between like 20 and 50% here. And so therefore, you're going to get a 20 to 50% difference in mass estimates here, which is huge. Again, that is a gigantic uncertainty in just how much our process material, our kilonova output into the universe, that can go into enriching our universe. So then we can also turn this around and ask, okay, I've been saying you get a difference in these observables, but what happens when we try to fit some data? What is the uncertainty there? And so again, I took the best data set that we have, GW170817, and fit all of my models to see what is the best fitting parameters that we can get, and look at the uncertainty between all of these atomic data set models. And so it turns out that your lanthanide fraction is very severely impacted here. 3/4 of an order of magnitude uncertainty between each of these atomic data sets here. And so that's something like a factor of 6, which again, just to kind of impress upon you, this means that we are uncertain by a factor of 6, purely from just atomic data uncertainties of what the lanthanide content of our kilonova are. Thankfully, it does seem that the total mass is conserved, and so, but there is still a little bit of deviation between each of our kilonova components, our red component and our blue component that I was talking about earlier. And then for the most part, our velocity, our characteristic velocities of our kilonova estimates is not as impacted by these things. So those are the main conclusions. And so I will leave up my conclusion slide. And thank you so much for taking time to listen to my presentation. And I'm happy to take whatever questions you might have.
Great, thank you. Thank you, Daniel. Any questions for Daniel? Please raise your hand or write in the chat. I think we have a Q&A option in the Zoom call. I'll start with one. I have a couple of naive questions, and one is, how do you confirm that our processes are occurring in a source? That's maybe too naive, but is it just by the detection of the lanthanides that already tells you that our processes must be taking place, or is there something more than that?
It is really that infrared excess, because there is no material that has nearly as high of an opacity in the optical and the UV as our lanthanides. And so if you undergo strong R process, then you will be making these lanthanides. And so you're basically guaranteed to see this strong infrared excess. And so that's how we know that that R process has occurred in our kilonova.
Great, thank you. I have another question, but I'll let other people to ask. I think Martin Lemming has his hand raised.
Thank you. Very nice talk. My question really is, what sort of charge states are the lanthanides that you're considering? What charge states are relevant here?
Yeah, these things are typically between, for the most part, singly up to like quadruply ionized, not a whole lot beyond that. Typical temperatures of kilonova range between like something 2,000 to like 10,000 Kelvin at the earliest times. Not once we start simulating them, I should say. It's much hotter, of course, initially after the merger event, but
a lot of the codes you mentioned are really geared towards much more highly charged ions than that. But I imagine for this application, you want the aggregate effect of lots and lots of levels and ions, and having extra precision doesn't really matter all that much. I mean, I used HULAC myself, and it's for X-ray applications mainly.
Yes, a lot of them definitely did note that they tend to be used for more higher ionization states, but the data sets that I was using have been particularly generated in order to be used for our kilonova opacity.
Yeah, okay. Great.
And so they were more geared towards those quote unquote lower ionization states.
Thank you.
So very, very quickly, if I can follow up on that question, maybe this is if this is discussed in your paper, I will go and read it, but can you mention what do you think is the main problem or that causes the difference between the atomic data sets? Because it's quite large, right? So is it the completion, the number of states, the levels that each one has, or is just the prediction on the rates?
It is, so all of these data sets have I wouldn't necessarily say a complete list of lines, but they do try to generate as many as they can. So I would say it's certainly not a fault of not having enough lines. The uncertainty largely boils down to just the complex interactions between all of the electrons in these elements, and a lot of assumptions that these codes have to make in order to be able to generate all of these levels, all of the transition strengths, all of that stuff. And so that's where you just get such a wide discrepancy in precisely where all of these transitions will be occurring, how often do they occur, and things like that.
All right, thanks. Any quick final questions for Daniel? Oh, well, thanks again, Daniel. Great talk, very interesting. Next speaker is Riley Connors. Riley is currently a postdoc and lecturer at Villanova University working with Joy Nelson's group. And he was previously a postdoc at Caltech with the NuSTAR group. And today he's talking about X-ray reflection, spectroscopy of accreting black hole binaries. Riley, go ahead. Not sure. You're muted, Riley.
Yeah, I'm aware. I'm not muted anymore. Can you hear me?
Yes, go ahead.
And you see my slides?
Yes.
Okay, yeah. I'd also like to thank the organizers for inviting me to speak. I really appreciate it. I'm going to talk about X-ray reflection spectroscopy of accreting black hole binaries and why we do it, and also what the sort of main recent results and steps we're making going forward in this kind of modeling. So of course you see an artist's impression on the slide of what a black hole X-ray binary is. You have a star and a black hole. The black holes are accreting from the star, and we primarily use X-ray studies to look at the very inner regions of the accretion flow. So why should you care about reflection spectroscopy? Well, we use it to measure black hole spin. That's one of the main goals of applying this kind of these kind of models. And recent results from LIGO have kind of thrown some of our understanding of what we're doing a little up in the air, because here they're probing a completely different, potentially completely different population of black holes. They're at least a lot heavier, but they're also much lower in spin, it seems. So, you know, in terms of X-ray binaries, reflection spectroscopy tells us that a lot of these black holes are spinning very rapidly, whereas LIGO sources, you can see in the bottom plot here, appear to have spins very close to zero. So what's going on there? Are these different populations, or is there something wrong with either set of measurements? Are there systematic biases that we're not really accounting for properly? So just very briefly, this is a toy diagram of a harness intensity plot of an X-ray binary as it's going through its outburst. These systems start off in quiescence, they rise through a hard state and shift across to a soft state. In the hard state, you see power law emission, we think that's coming from a corona. Soft state, you see a disk. There are states in between, but I'm not going to get into those details. And reflection modeling is sort of best applied in this hard spectral state where you see just pure power law emission. It's sort of a cleaner signal, and that power law is being reflected off the disk. You typically see quite strong reflection features here. But you see reflection features often throughout an outburst, not in every single case, but quite a lot of the time. And there are some open questions here that make determining black hole spin from reflection modeling kind of difficult. We don't know the structure of the accretion flow and the corona. We don't know the geometry there. There's this issue of disk truncation. So whether the disk is really right there at the innermost stable circular orbit, which you need to be the case to reliably measure spin. And in a lot of cases, we actually don't know really what the full continuum actually is. Okay, what are all the spectral components there? Because this matters for doing this kind of modeling. Entangling things is not easy. So just very briefly, this is an example of an application of reflection spectroscopy to X-ray data. So this is GX339. It's a very, very frequently studied source. It goes into outbursts quite often. And you're looking at NuSTAR and SWIFT data of an observation in a hard state. And you see a few different components. So you have the coronal component in blue, that's the power law. This purple component is the disk, which is quite weak because we're in a hard state. And then you see two reflection components, right? This distant reflection is the reflection that you would expect if you don't really have many relativistic effects, right? So you see this strong ion emission line, Compton hump, you see an edge feature as well. The red is a relativistic spectrum where all of this stuff's been smeared out. And I want to emphasize it's important that it's not just, we're not just modeling an emission line here. You're modeling an entire spectrum. So broadband coverage is quite handy for this. And this is the model being applied is RELSA, which is a very popularly used model. And you've seen an explosion in applications of reflection modeling to many different data sets in recent years. And some interesting findings have come from that, of course, is to update our models. So one example of that is improvements to the treatment of the density of the accretion disk, because this matters for what emerges in terms of the reflection spectrum. The genesis of these models assumed a fixed density, just one number, 10 to the 15 particles per centimeter cubed. This is sort of in the ballpark for applying this kind of model to an AGN disk, but since the density goes inversely with mass, black hole binary disks are expected to be much more dense, perhaps even above 10 to the 20, so many orders of magnitude. In combination with the fact that when applying these reflection models, we were finding that the iron abundance that we needed to fit the strong features that you see in the spectrum needed to be very high, often more than 5, even 10 times the solar value, which seems unrealistic. So the idea here was that, perhaps a better treatment of the density replaces that need for high iron abundances. And models were developed in 2016 to include some effects of increasing the density. I won't go into the details, but some effects were included. The primary outcome of that was that you get some softer emission due to free heating of the electrons. So it does change the spectrum, and it has been applied to several sources since then, and we've learned a few things. It seems perhaps to replace the need for elevated abundances, for example. But these calculations didn't include all the possible effects. There's more atomic physics needed there. And so that's what has been happening in recent years. So this is work by a student at Caltech, Wanzhe Ding, who has been exploring all the additional effects in terms of the atomic physics that you would need to include as you go to higher densities. And he's shown with his calculations that you can actually get some pretty substantial change to particularly the ion emission lines, mostly the ionized lines. So high density models do seem to replace the need for elevated abundances, and now these effects are starting to be included in the models going forward, and I'll get into that again a little bit later. Here's another key result that occurred from applying reflection models in the last five years or so. So this is a source that was in a very soft spectral state. This is actually RxTE data, but very, very high signal to noise. What we were finding here is that applying standard reflection models, so the baseline continuum is a power law in RelSil, and you're assuming there really that you're in a hard spectral state. And what happens when you're in a soft spectral state like this is often you find you don't really have the power law signal to produce enough reflection. So the model sort of skews into a weird area of parameter space, doesn't quite fit the data very well. So we thought, okay, what if we're in a soft state, we have a strong disk component. What if the reflection is actually coming from a black body? Okay, and we applied this model instead. You see that on the right hand side, and it does a better job. But more importantly, it kind of works energetically. And we thought, okay, this could actually be what's called returning radiation. So you see a diagram of that here. You have photons that are coming from the very inner regions of the accretion disk. These are thermal black body photons, and they're being bent back to the disk itself. And if that component is strong enough such that the returning component is actually brighter, or there's higher flux there than is in the coronal power law, which may be the case in soft states, and it's indeed what we think we've found in a few sources, then we could actually be seeing the reflection signal from this dominating things. So that's something we're now looking to build into reflection models. And a curious note on that I thought I should mention is that IXP, with its polarization measurements in the soft X-ray band, is typically finding when they observe in soft spectral states that there's a need for very high levels of this returning radiation. And I wanted to make a note on that. So first of all, of course, that's interesting for us, but also I think what we really need to start doing now is matching that up with what we see in the spectrum. So when we're seeing this need for a lot of returning radiation in polarization measurements, is that required in the spectrum? Because you may expect from what we found that you actually see quite significant reflection. So yeah, something to check for consistency wise. So a final thing I'm going to discuss in terms of new model developments and additional things we've found in very high signal to noise observations is this concept of plunge region emission. So I mentioned that we're doing reflection modeling, we're relying on the fact that the disk hits this inner most stable circular orbit. But what if we're seeing emission from stuff that's falling in? So gas that's gone through the ISCO is plunging into the horizon. Is that negligible, the emission that you would get from that? And it seems like that's not actually true. It may be meaningful, it may be important. And this is an example of that you see here. on these three different diagrams, you're just looking at an X-ray spectrum in a sort of soft-ish spectral state of Maxi J1820. And you can see I've sort of highlighted it with these orange boxes, this additional signal beyond just a disk and a power law that doesn't look like reflection, it doesn't look like an emission line, it looks like an additional continuum component, and it's pretty well modeled by a black body. So the idea here is that this actually may be thermal emission from that plunging gas. And Andrew Mummery has recently published a paper demonstrating with proper physical calculations that this may be the case. So it actually sort of checks out. So it looks like we can actually see emission from this gas falling in. But what if that gas is also reflecting X-rays? Right. So a student working with us at Caltech in the last few years, Jameson Dong, has been doing these calculations, looking at, well, if that gas that's falling in is dense enough, if we assume it's dense enough and there's enough material there, will it produce enough reflection that we'd actually see it? And I'll explain in a minute why this is so important. It looks like from his calculations, at least, you see enough that this will give you a different shape to your reflection spectrum. It will actually give you a broader line than you would expect if you ignored that emission. So it looks like it's important, particularly at low spins where the ISK goes further out. And so there's more plunging region, basically, in terms of there being about several RG of gas that can reflect. Student of mine, Merjan, an undergrad student who worked with me this summer, has started to actually take these models now and test whether ignoring this effect would have potentially biased spin measurements. So this is, as I mentioned at the beginning of the talk, this is an example of something that could have been a systematic bias that we have been ignoring. And she's found that actually it could be quite a substantial effect. So as you go down to low spins, when you apply a reflection model that ignores reflection from plunging gas, you could be significantly over predicting the spin. So if you look here at, for instance, an input spin of 0, where you include that plunging gas, you'd get a measurement of roughly 0.5. I mean, that's quite significant. Now, of course, the effect is less important at higher spins, but this is meaningful. I want to stress, though, that this is preliminary work, so we need to dig into this a lot more before it turns into a paper. I just want to give a couple minutes on the future of this, and I think I want to stress that CRISM is really going to make a huge step forward, huge leap forward in terms of how we understand reflection spectroscopy and the kinds of constraints we can get. And obviously there are unknowns there. The resolution is so incredible that we don't know really whether we're going to find that we have to throw out certain elements of reflection models or completely change them. I'm showing here just a couple simulations. On the left-hand side, this is 4U1630. It's a source where, with NuSTAR observations, we found that you have a wind component there, you have some absorption. It's a soft spectral state, so we typically see winds there. But you also have some evidence of weak reflection. And but it's difficult to disentangle these components. CRISM won't have that problem, basically. It's got enough, certainly enough resolution, but also enough sensitivity. That's another key thing there. So you've got sort of enough broadband coverage and sensitivity to actually constrain the reflection component. And of course, there's the chance to have simultaneous measurements, and the way that we'll be able to separate these components has not been possible before. And on the right-hand side, I'm just showing how CRISM will be able to disentangle the relativistic component from what we typically see, which is an additional distant component, so a narrower component. And there's some nuance there. I'm showing sort of the extreme here, but you can see CRISM in that bottom part of the ratios panel. It will clearly distinguish these components, and that applies also to these high density effects. So this work that Wanzhe Ding did recently, he performed some simulations to demonstrate that CRISM will be able to tell the difference absolutely between these higher density models versus the lower ones. So when you include all these atomic effects, CRISM will be able to tell us, really, we measure the actual density because of these elevated strengths of the emission lines. I want to give a nod to HEXP. Of course, we've just recently found out, sadly, it's out of the running for the next X-ray probe. But yeah, this I just want to stress that having a mission with broadband coverage and high sensitivity out to higher energies very key for reflection spectroscopy. So of course this was sad for us, but congrats to Axis. And just before I finish, I just want to make one last comment. Reflection features, I said at the beginning, are often present throughout an X-ray binary outburst. And when we see that, of course, the temptation is to throw reflection models at it. And I think you really need to be careful. So on the left-hand side here, I'm showing the equivalent width of the ion emission line that you see across all the spectral states. So the x-axis is hardness. The features can be quite strong as you go across to a soft state and through these intermediate states, but the continuum is less certain. And so just blindly applying reflection models here can give you very strong systematic biases. On the right-hand side of some really good work by Paul Dragis, where he applied reflection models to many, many sources. And here I'm showing some spin constraints versus the disk inclination parameter of the reflection models. And you see this very strong correlation and a sort of distinction depending on the spectral state of when you're applying just one model. So here you see you can get really strong systematic biases from just applying the same kind of model to very different regimes. And I'll just leave my summary slide there and take questions.
Great, thanks, Riley. We run a little bit over time, so we have time for maybe one question. Not see any hands. Oh, there is somebody. Scott.
Hi, Riley. That was a really great talk. I was wondering in the intra-ISCO emission modeling that you were doing and how it creates a bias and spin. How does that compare with the Schnittman 2016 analysis that did similar things with GRMHD simulations?
I think I'm familiar with the paper that you mentioned, but I'm honestly not sure. I don't remember off the top of my head the specifics of what kind of biases they found. So in order to answer the question, you might have to refresh my memory.
Well, I have to refresh my memory too, but we did similar work by exploiting GRMHD simulations that don't assume anything about the flow within the ISCO. So it'd be interesting to see what your model, how they compare with our simulation-based models.
Yeah, definitely. I'll have to go back to that paper. I mean, there's not only that, but other work that I've seen coming out recently that we do need to have a look at to compare what we're finding. This is something we really need to dig into a lot more. It's very preliminary work, and I mean, the main thing is we didn't really expect that the effect would be so strong, but it is also based on very particular assumptions, right? So here we're really assuming that the disk is just a constant density all the way down to the horizon of the black hole. And that comes from, basically comes from MAD simulations, where it seems like it's possible to have a disk that stays quite dense down to those radii. But of course, that may not be the case. So I think we want to start exploring what happens to these constraints under different conditions as well.
Okay, great. I think we're out of time, but if there are more questions for Riley, just please write it in the chat and he can read them there. Thanks again, Riley. So now we have the last speaker, but not least, is Nicole Rodriguez Cavero. Nicole is a graduate student at Washington University in St. Louis, working with Professor Henry Kruczynski. She works on X-ray polarization measurements and is a member of the IXP collaboration. So Nicole, take it away. And I cannot hear you right now. Maybe you're muted.
Can you hear me now?
I hear you now. Yes, great.
Okay.
And
awesome.
we see your
Thank
slides.
You.
Yeah.
Okay, cool. So yeah, I will be talking about observations of subatomic black holes, specifically with the Imaging X-ray Polarimetry Explorer, or IXP for short. So just as a small background, we know that there's different black hole components, and each component has a very distinct type of emission that we see in the X-ray energy spectra. From the accretion disk, we see typically this black body emission component, and then emission that comes from the disk and is repeatedly Compton upscattered in some optically thin plasma region is the Comptonized emission. And then Comptonized emission being reflected back onto the disk and the observer is the reflected emission, giving rise to features like the iron K alpha line at 6.4 keV. So black holes can be found in different states of accretion, predominantly the soft and the hard state. And each state will have a different contributions of the three emission components that I mentioned before. In the soft state, we usually see predominantly this soft component over here coming from the accretion disk and peaking at around 1 keV. And the hard state is mainly dominated by this Comptonized and reflection emission, creating this Compton hump over here and the iron line over here. So depending on the spectral state in which we observe a black hole, polarization can give us different clues about the properties of the black hole system. For example, in the soft state, dominated by thermal emission, polarization can help us constrain the black hole spin and inclination, which I will discuss in a little bit. And in the hard state, which is dominated by coronal emission, polarization can help us study precisely that, the corona. So over here, I am showing some ray tracing results from Schnittman and Krolik 2009, just to show what the different components in the states would look like. These black vectors are length is the polarization degree and orientation is the polarization angle. So for emission that comes directly from the thermal accretion disk, we expect polarization to be directed parallel to the accretion disk. For returning radiation, which comes directly from the disk, but is then gravitationally lensed around the black hole and bounces off the accretion disk, we expect this to have a higher polarization degree and to be polarized perpendicular to that of direct thermal emission. And then for the hard state, for polarization that comes from multiple scatterings in the corona, the polarization direction is considered to be perpendicular to the scattering plane of the corona. In the case of the simulations, they used wedge-shaped sandwich corona, which is over here. Therefore, the polarization is perpendicular to the accretion disk. Of course, there's different coronal geometries, and before XP, we did not have a clear grasp of which geometry to have some inclination towards. There's the lamppost geometry, which is favored by time lag analyses, where you have some coronal region in the spin axis of the black hole. There's also a sandwich corona encompassing the accretion disk, the truncated disk hot inner flow, where the disk is truncated and then possibly owing to evaporation turns into some corona in the hot inner flow, and a spherical geometry. As I mentioned before, polarization and inclination and spin are closely related. To the left over here, I'm showing the results from Chandrasekhar for pure electron scattering atmosphere. And you can see that the polarization degree tends to increase with higher observation inclination. And for spin over here, I have some results from also Schnittman and Krolik, which shows that depending on the spin of the black hole, the polarization degree will also change. In this case, the solid lines are showing direct thermal emission, and the dotted lines, well, it's also thermal emission, but this one is including higher effects of returning radiation because the spin is higher. And since they're polars perpendicular to each other, they tend to cancel out. So the Imaging X-ray Polarimetry Explorer, or XP for short, was launched on December 9, 2021, and it is a collaboration between NASA and the Italian Space Agency. Now, we really like IXP because it provides simultaneous spectral, temporal, and polarization measurements of astrophysical sources. And polarization is really essential for determining the geometry of the spacetimes around black holes. So far, IXP has observed 9 accreting stellar mass black holes, and today I'm going to be talking about some interesting results. So starting off with Cygnus X1, our first observation of an accreting stellar mass black hole, actually. And we caught Cygnus X1 in the hard state, where we expect coronal emission to dominate. We measured a polarization degree of around 4% at a polarization angle of minus 21 degrees. And as you can see on the left over here, there was a clear relationship between polarization degree and the energy band in which the source was observed. And the polarization angle seemed to be relatively constant with respect to energy. Now, what we did is we compared the polarization angle with the direction of the radio jet imaged by the Very Large Baseline Array in the plane of the sky, and we found that they were approximately aligned. Now, previously I had said that we expect the polarization of the coronal emission to be perpendicular to the scattering plane. For us, this meant that we could rule out vertically extended corona models in favor for laterally extended ones, such as the sandwich corona model and the truncated disk one, in order to accurately replicate the polarization direction of the observation. Following this constraint, 2 years later, we observed Cygnus X1, but now in the soft state where thermal emission dominates. And we were able to determine that some degree of coronal contribution and returning radiation is necessary to replicate the polarization degree, which was around 1%, I believe. Something interesting, though, is a postdoc in our research group was able to determine that the corona optical depth has to change significantly in order to accurately model these results. And so what this translates to is as the polarization degree decreases from the hard state to the soft state, this can be equated to coronal optical depth decreasing and the corona thinning out, which is really nice to have a relationship between the polarization degree and the accretion states. Next up, I wanted to talk about this black hole. It's called 4U1630-47, and this one's kind of an outlier in our results. So we first observed 4U1630 in the soft state, thermal emission dominating, and we found an unusually high polarization degree of around 8%. As you can see over here, we go from around 6 to 10 in polarization degree across the IXP energy band, with the polarization angle still being relatively constant with respect to energy. Now, in order to account for the high polarization degree of this observation, several methods had to be taken into account. For example, we know that a partially ionized atmosphere increases the polarization degree. We also know that a vertical outflow velocity near the system of the thermal emission increases the polarization degree due to aberration effects having an effectively larger inclination angle, which increases the polarization degree. So we were able to replicate the observation polarization degree by invoking a model of partially ionized slabs, which again made it so that the polarization degree would be higher than in your standard thermal accretion disk model. And these results were able to model the observation successfully for an inclination of 75 degrees and a quite high outflow velocity. Then we returned to this black hole again, but in the steep power law state. So I talked about the soft state and the hard state. The steep power law state is an in-between state where instead of having one dominant contribution from thermal or Comptonized emission, you have both components. And here you can see the soft state observation in black, which looks pretty thermal, black body-like spectrum, and the steep power law state one where you have this additional power law component over here. And as you can see, the hardness ratio increased and also the intensity. So for this steep power law state observation, the polarization degree was slightly smaller than the 8% that we saw in the soft state, and it was 6.8%. And this is a comparison between the soft state observation and the steep power law one. As you can see, the polarization angle only varied within 3 sigma, and the polarization degree decreased slightly. Now, these results were very puzzling to us at the time because we added this whole new power law component into our emission, but the polarization angle did not change significantly. And we usually expect like a power law emission and the thermal emission to be polarized perpendicular to each other. But the polarization angle didn't change. So this told us that for this observation, both the thermal and the power law components had to be polarized in the same direction. And so in this case, what this translates to is that both emission processes for the soft state and the steep power law state need to be similar to have the same polarization characteristics, but perhaps with different scattering mechanisms. And this is a change from primarily elastic Thomson scattering in the soft state to inelastic Compton upscattering in the steep power law state. So what we propose is that for the original ionized plasma atmosphere that we see in the soft state, if there's a heating in the environment, perhaps due to a lack of shocks or magnetic reconnection, this will change the atmosphere into Compton temperatures, and this will create that power law component that we see without changing the polarization angle of the system. Next, I want to talk about Swift J1727. This source was discovered last year, and it was a really exciting source because IXP was able to catch it during the whole like hard to soft state transition and then back to the hard state. It is brighter than any other black hole that we've seen outburst recently in the X-rays. And IXP conducted 5 observations on the source, like I said before, in the hard state, intermediate state, soft state, and the intermediate state, but from the soft to hard state transition. And to show some polarization degrees results, in the hard state, the polarization degree was around 4%. So very similar to the hard state observation of Cygnus X1. There was an alignment of the X-ray, optical, and submillimeter polarization angles, and we found similar coronal properties to that of Cygnus X1. Now, given the polarization degree between this source and that of Sig X1 was really similar, this allows us to set a big constraint on the inclination of the system to be intermediately constrained from 30 degrees to 60 degrees. Next, we caught the source in the hard to soft state transition. So on the left over here, you can see the first observation, and then you can see the hardness and the flux decreasing during the transition. And conversely, we see the polarization degree also decrease as time goes by through this transition. So we see that the average polarization degree is decreasing. However, the polarization angle still seems to be relatively consistent with respect to the change in state. Finally, when the source was in the soft state, we noticed that the polarization degree decreased quite significantly. And this is exciting for us because it matches Chandrasekhar's predictions of inclination and thermal emission polarization degree. And this tells us that polarization degree is indeed very sensitive to the accretion state of your black hole. Additionally, we had previously set this constraint for the inclination of the system, but this lower polarization degree tells us that the inclination has to be on the slightly lower end because this is not a polarization degree that you would see in the soft state with a high inclination of 60 degrees. So this shortens the constraint a little bit, but it's really exciting to have inclination constraints from purely polarimetric results. And with more observations, we will be able to keep narrowing these constraints down. And then we caught the source on an intermediate state from the soft to hard state transition, and something very curious happened. So in the soft to hard state, the transition, the polarization degree was around 3.3%. Now over here, you have the bright hard state, which is the initial group of observations for the system. And down here, we have the dim hard state. The luminosity between these observations differed by 2 orders of magnitude. However, we see that for both transitions between states, the polarization degrees are pretty much the same, and they have the same polarization properties. So this tells us that the accretion properties of the system and therefore their polarization must be the same regardless of the luminosity of the object. So we're currently wrapping our heads around all of this new cool results, and we're investigating what we can learn from polarization in regards to the accretion states of these objects. So as a small little summary, we've observed 9 accreting black holes, 4 of them in different spectral states. Some of our surprising results was that polarization degree increased with energy even more than we expected. A couple of sources, 4U1630 and Cygnus X3, tend to be outliers when it comes to your average accreting stellar mass black holes. And our main result is that we've been able to observationally prove what the geometry of the corona looks like. And for a couple of sources, we've been also able to constrain their spin purely from polarization data. Thank you.
Thank you, Nicole. This is a great review. We have time for maybe 1 or 2 questions. We're almost at the hour. Anybody wants to raise their hand, please? Or write in the chat. Yes, right.
Nicole, great talk. I just wanted to ask about, I mean, I mentioned it in my talk, this returning radiation requirement in a lot of not every source, but a couple of the sources I noticed, the papers that came out. Can you just give a comment on that? Like, does that complicate things in terms of constraining the spin from polarization, or does it? I mean, it's an additional component there that's competing with other components, right?
Correct. Let me find that slide that I hid. Okay, I'm gonna unhide it. Yes, of course. So in the case of 4U 1957, we were able to constrain the spin a little bit. And so what you're seeing here is the albedo parameter, which directly translates into how much returning radiation we're going to see. For the purpose of the simulations, these arrows over here show approximately the increase that the IXP data had between polarization degree and the energy band. And as you can see over here, some degree of returning radiation is required in order to be able to explain the high rise of polarization degree with energy. So I would say, while we will see some canceling out between the polarization between returning radiation and direct thermal emission, understanding the polarization of returning radiation will eventually help us narrow down the spin of the objects.
Okay, I'm afraid we are running out of time. We're almost at the hour. So I'd like to thank Nicole and Daniel and Riley for great presentations. Remember, all this was recorded. The videos of the seminars are posted in the online in the website of this seminar series, which you can find right now in the chat. And please keep sending us your suggestions, your nominations for more talks. We'll hope to see you next time, maybe in a couple months from now. Have a good rest.